Let's continue on Workbook 3 by learning about spectra. Now remember from the last video, this is where we left off, was that electrons can only accept certain levels of energy. So this is a diagram from your book. Let me zoom in a little bit. It's a little bit shiny. I don't know what's going on there, but you can see that this is the same as this diagram over here, figure 5.12 in your book. So what's going on here is you can see that the electrons can only accept certain amounts of energy. So for example, for this particular electron, for this electron to become excited, in other words, go up a level, it can only accept 10.2 electron volts. That's all that it can accept. It can't accept 11, it can't accept 5. 5 isn't good enough, 11 isn't good enough. And we use this analogy that instead of thinking of this as like accepting energy, think about it as a key and a keyhole, where the key is this energy and the keyhole is these these levels, these ionization levels of the electron in the electron shells. So really picturing it as one is a key and one is a keyhole and they only fit together one way is important for understanding this. Now this would be a good time for you to track down your colored pencils. And when you do, we're going to have a quick review of a concept you probably learned back in grade school. So go ahead, take a moment, track down your colored pencils. So spectra, in other words, the light produced and the colors that light produces, colors that are part of that light, of astrophysical objects are usually a combination of these three basic types. And these are going to all be definitions. So I'm just going to go ahead and I'm going to underline each one of these in red. So first one is continuous. And a continuous spectrum is a spectrum produced by an incandescent object. And it helps now to have incandescent. So I'm a big fan of stems. Canned, this is actually means candle. This is from candle. So an incandescent object, incandescent, means that it's so hot it's glowing. And really, as we're going to learn about in thermal radiation, everything above absolute zero is hot enough that it's going to be producing some sort of spectrum. So, but in this case, we're talking about a very hot object producing a continuous spectrum. So a continuous spectrum looks like a rainbow. Or more accurately, a rainbow is an example. A rainbow is the continuous spectrum produced by the sun. Now I'm going to use my straight edge right here. And it's always helpful to, because Roy G. Biv is 7, right? 7 letters. So you may want to, for example, use 14 centimeters. That might be helpful. Or 7 inches might be a good way to mark it. But you want to have it in such a way that it's kind of evenly spaced. So it doesn't need to be perfect, but it's definitely going to help if it's a little organized. It'll help it stick better. Drawing is learning, my master's advisor always said. So my master's is in geology, and he advocated for a lot of sketching, and I can definitely say that when you draw out your ideas, you definitely learn it better. So I'm just marking this off into 7 sections so that I can color this in. And this is, the continuous spectrum is a rainbow. So that's just going to look like Roy G. Biv. Okay, so take a moment to fill that in right now. So you have, wow, the magic of film. So I have that colored in now. You didn't have to wait and watch me color. Happy little, in classic, happy little rainbows. So this is our happy little rainbow right here. And we're going to be using this rainbow later on down here and down here. So we're going to just take this little box, however you drew your little box here, we're going to transition it down here and here. We're going to make the same box. I made it like this. So I'm just going to draw literally the same box down here. So see how I kind of extended it downwards? So making foam in real time. Ignore those smudges. And yours doesn't have to be perfect. Mine most certainly is not. But you do want a good approximation of this box down here and lined up. We'll see why that is in a moment. Good approximation down here. And we're going to even extend those little, see those little dots that we had above? We're going to extend those down here. All right, so you see that the box pattern is the same. I'm even going to enter in my Roy G. Biv along the top and my Roy G. Biv down here. So these should be matched up together. I'll give you a moment to do that. So the emission line is the pattern of spectra, or the spectrum, produced when an electron falls from a higher level, emitting a photon. Okay, so remember back in our keys and our keyhole idea over here, okay? We only have certain keys and certain keyholes that work over here. This right here, this basically, if we think of this as the key and the keyhole, this is the key that fits into the keyhole. So these are the ones that are these are the electron packages being released when this exactly 10.2 electron volts being released when this electron falls from here to here. So this is the key leaving the keyhole. All right. So basically that energy leaving that keyhole. So what's that going to look like? Well, you have some great diagrams in your book, including here on figure 5.16. We're going to recreate helium, both for the emission and the absorption lines. And I'm going to try and zoom this in a little bit. Okay, so you're going to see that there's particular lines of color. Now the thing is, this is unique for each element. So this pattern of helium right here is basically a fingerprint for helium. So we can see that there's, and I can see also that I did this backwards from them, so we're going to just draw it over here, that helium has a line in the red. I'm going to grab my red pencil. Where is my red pencil? There is my red pencil. It has a line in the red. I'm going to draw a line over here for the red, for helium. A line in the yellow. So I'm going to draw a line in yellow, in my yellow color. 2 lines in my green. Pretty close together. A line in my blue and a line in the darker blue. So this right here is the emission spectrum for helium. And this is really helium, the elements. It's used as helium's fingerprint. So if we look at this spectrum in space and we see a spectrum that matches this pattern in space, we know that helium is present. Now the absorption line is related to that. So the absorption line is the spectrum produced when photons are absorbed in or by atoms in a cool gas. So we'll see this and this once again, this is something that's discussed in your book very well. Well, not perfectly great. That's one of the reasons we're going over this here, and we'll talk about this diagram in just a few moments, but this is nicer because it's in color. Basically, you have that continuous spectrum going through the cloud of gas, and that cloud of gas is only absorbing certain parts of the spectrum. So in this case, this is the key leaving the keyhole. This is the key entering the keyhole. And a key, once again, being that energy level. Now, what is that pattern going to look like? That pattern is going to be this same pattern up here. We're going to do helium absorption. But it's going to be the opposite. So these colors are usually not against white, they're against black and darkness. But this is the opposite of that. It's going to be basically a rainbow with little slices taken out of it. And the slices are going to match up to the same spot because of the same keyholes, right? Same keys, same keyholes. So we're going to start by coloring this in because really what you can think about this is that these are the keys disappearing from the continuous spectrum. Okay, and once again, we'll talk about it a little bit more when we look at the other diagram. So I'm going to let you first start by filling this in as a rainbow up here. We're starting off with this being a continuous spectrum. The magic of film. So we now have our rainbow colored in, and now we're going to slice out those little keys. And I'm just going to line it up exactly like we did here. Okay, whoop. I need to get something black. We're just going to basically like imagine cutting out that little keyhole here. Okay. Same too with the yellow. Line it up exactly. Cut it out right here. See how it gets removed? Same with the green. Now, don't tell Professor Shabulu about this because he's going to be like, this isn't technical and this kind of stuff. But what I'm worried about, it's not perfectly scaled. It's not perfectly scaled. Let's be real. But the important thing is you'll understand it at the other end of this, which I like understanding things through simple drawn cartoons. Ask anyone that takes my classes. There's a lot of little art things involved. And I feel like this is a good way to understand that these are directly related. This and this are basically the same thing. This just getting absorbed, this getting released. So let's go ahead and take a look. Take a moment if you need to fill out your page right here. And now I'm just going to flip over and go to the next page in the notes right here. Okay, this is the same as this diagram figure 5.14 in your book. And so what we're looking at here is where am I actually going to see this pattern right here? Where is that coming from? So the first one, this is where you're going to get your continuous spectrum. And this is from a light bulb producing all the wavelengths. So this is a hot light bulb. This is an incandescent bulb, an old-fashioned light bulb. Okay. That gets sent through the prism, and the prism is producing the continuous spectrum here. Once again, back on this page, it's a little bit easier to see because it's in color, but I didn't want everyone's color printer to get devoured, so I converted this to black and white. Now, in this next one, this is where you're going to see the emission. Okay, this is the key leaving the hole. This is the energy being released. So you have this cloud of gas, okay, that is warm, and that warm cloud of gas is releasing those excited, see the heat in that gas is making the electrons all excited, but they're like electrons are like your 4-year-old. Gets real excited but can't hold it for long. So it goes and flops over. Okay, so these electrons here get exactly just like your 4-year-old. Gets really excited but not for long, and then it's down. Okay, and when it drops that energy level, that's when it releases these photons of these levels. Because remember, we learned back just a few minutes ago, not a few videos ago, that you can directly tie the color of light, the wavelength of light, to that wavelength's energy. Those are intimately tied to one another. Okay, so that's what's being released. Now over here, we have the absorption, I always spell this, okay. This is taking it in. So this is taking in those photons. So this hot source of light is a continuous spectrum. This cloud of gas absorbs certain wavelengths. And these black lines over here are those missing wavelengths that have been absorbed. Now, if you find this a little bit challenging, you're not unique. Most people, including me the first time I bumped into this in chemistry, found it a little bit challenging. So don't be afraid to ask me questions or rewatch videos. Now, we're going to talk about a different concept that's also related to light and energy and temperature, and that is thermal radiation. So this thermal radiation, okay, the definition, so let's underline it here. Thermal radiation, objects will emit a continuous spectrum. And what was a continuous? We'll go back. We'll analyze this, what we mean by continuous spectrum of thermal radiation that peaks at a wavelength determined by temperature. So, the higher the temperature, and the big key here is the higher the temperature, the shorter the wavelength. The lower the temperature, the longer the wavelength. Now, this goes back into that red-blue idea and purple and all that other kind of stuff, okay? If we look back at these notes over here, okay, with the rainbow, we can remember over here that these are long wavelength. We saw that in that one video. And that these are short wavelength, right? So if we have higher temperatures, we have shorter wavelengths. So, for example, let's suppose, compare an imaginary purple imaginary violet star and red star. Which one has a hotter surface? So take a moment. I'm going to Dora the Explorer this. Imaginary violet star and red star. Which one has a hotter surface? Which one do you think? If you said violet star, you are correct. Because violet has a shorter wavelength. Violet has a shorter wavelength. So this points it out in your book. At relatively low temperatures, the poker only emits in the infrared that we can't see. That's very long wavelength. And it goes from red to white as it gets shorter wavelength. / hotter. So that's what's going on here in this diagram here. We're just talking about the two laws of thermal radiation. The curve for the hotter object everywhere above the curve for a cooler object, okay, showing that hotter objects emit more radiation, and that the peak wavelength is further to the left for hotter objects, showing, in this case, left is, it's not just left, it's shorter wavelength. Then it shorter showing that hotter objects emit more light at shorter wavelength. So basically what we said, this graph is saying exactly what we said over in the previous, that's what we said right over here.